Hi folks, and welcome back to Math with Captain Rod. The purpose of this video here is to go through an example of optimization here. And this example is basically pretty close to number 14 in the current calculus text I'm using here. But what we're looking at here, I've kind of modified this in honor of the upcoming elections here. What we have here is we have Donald Trump, who has taken over a factory which produces beer cans. And he's told the crew, hey folks, you got to build a cheaper can or else we're going to have these cans made in China. So the idea here is that we want to be able to build this can that holds 1,000 cubic centimeters. And we want to make it as cheap as we can. Now when I say cheap as we can, the cost of the can is going to be based on the amount of material. And the material, how much material we're going to use, we're going to measure by the surface area of the can. So the first step in these problems is to always identify what is it we're trying to optimize. In this problem here, it's area. We want to build this can that holds 1,000 cubic centimeters using the least amount of area. So the area of the can is what we're trying to optimize. Now, I'm going to go ahead and write an equation now for the can. The can has a certain height here. I'm going to call that h. It has a certain radius, r. We're going to have to define the dimensions of r and h. That will minimize the area. Now the surface area, we've got a side surface area. The surface area of the round part of the can is going to be 2 pi r times h. The 2 pi r is the distance around, like this, times h gives you the area of that side surface. The top has an area of pi r squared. And there's two of them. Whoops, get that so we can see that. So pi r squared for the top, and there's two of them. So the can has a total surface area equal to 2 pi r h plus 2 pi r squared. So here's our function we're trying to optimize. Before doing so, however, we're going to have to get this down to one variable. Right now it's a two-variable problem. We don't know r, we don't know h. That's where we can use some fact from the problem here. In this case, that can has to hold 1,000 cubic centimeters. The volume of the can is equal to pi r squared times h. All right, so for those of you who aren't super familiar with geometry, you can get volumes by taking surface areas and multiplying by the third dimension. So that's how I got the volume of that can. Now in this example, the volume is a fixed numerical value of 1,000. It's 1,000 cubic centimeters. I'm going to leave the units off for now because I don't feel like writing them over and over and over. Now, the next step now is to eliminate a variable. We can either eliminate r or h. It doesn't matter which. I think I'll go ahead and eliminate h. So h is going to equal 1,000 over pi r squared. So now anywhere we see an h, we can put 1,000 over pi r squared. So I'm going to go ahead and take this and sub it into my area function here. So our area now is going to equal 2 pi r times h, which can be written 1,000 over pi r squared, plus 2 pi r squared. I'm going to go ahead and clean this up now a little bit. So the 2 times 1,000 is 2,000. These pi's will cancel or reduce. R over r squared is going to give me a 1 over r, and plus 2 pi r squared. So here's our function that we want to optimize now, written in terms of one variable. I'm going to take a moment here and clean this up. Let's see. I don't think I need this anymore. And I'm going to take this, just move it up here. So here's our function we're dealing with. Now, wherever possible or practical, graphs are always, really nice things to have. I'm going to just take a moment and sketch a little what I think this thing looks like. So for starters, this thing's isn't defined at r equals 0. It's asymptotic there, and that's okay. I'll just put my sketch over here. And again, this is just meant to be a quick little sketch. Doesn't have to be perfect. Feel free to use a graphing calculator to help you with these sketches, I think, if you're having trouble. But this thing's asymptotic. It's probably looking something like this, almost certainly, because it blows up as r goes to 0. So I know as I approach the asymptote this way, this has a vertical asymptote, so that's how I know this thing's going up. I know because of this r squared, as r goes to infinity, r has to also be increasing. Or I'm sorry, as r goes to infinity, the area goes to infinity. So I know it's got to look something like this. This is the point we're looking for right there. And at that point, the tangent line has 0 slope. So we need to look for the point where dA dr is equal to 0. When we differentiate this function, its derivative is minus 2,000 over r squared. That's coming from, effectively, this is r to the minus 1, and applying the power rule. Or you could use the quotient rule on this, either one. 2 pi r squared has a derivative of 4 pi r. And again, we're looking for where does this equal 0. So we've got, let's see, to solve this first step, I would do is multiply it by r squared. So the next line is going to be minus 2,000 plus 4 pi r cubed equals 0. So r cubed is going to equal 2,000 over 4 pi. So the radius that is going to optimize us, give us a minimum area here. I'm going to wait for one of my assistants here to calculate this. Would somebody please take 2,000 over 4 pi, make sure you put this in parentheses, hit equals, and then raise it to the 1/3 power to give me a value for r. What's going to be? 159.2 centimeters. I'm going to wait a moment here for another opinion. Did you remember to cube root it? Raise it to the 1/3 power? That sounds awfully large. I don't think that's right. That sounds about 5.42. Okay, 5.42 centimeters. That's okay. So some possible things. Make sure that this 4 pi ended up in parentheses when you divide, and then raise the entire thing to the 1/3 power. But the 5.42 looks good to me. We can go ahead and get the height from an equation that I erased, but the volume, which was 1,000 cubic centimeters, was equal to pi r squared, that's 5.42 centimeters squared, times h. Would somebody please take this 1,000 and divide by pi times 5.42 squared? Being sure you put this entire thing in parentheses when you do the division. And what do we get? 34? 34 centimeter. Anybody else get that, just to confirm? I'll get one more opinion here before we move on for H. 34. Okay, so now if it's wrong, it's your guys' fault, and you're fired. All right, so let's see. It looks like dimensions of 5.4 by 34 should minimize the surface area that can. We can go ahead and calculate a surface area now just to see what we get using any of our previous work here. I'm going to go ahead and use this. So the area should be 2,000 over, and that's going to be 2,000 square centimeter over r, 5.42 centimeter. I'm just going to leave out the units for this calculation. So there's our 2,000 over r plus 2 pi times r squared. I'll just do this. Units will come out in square centimeter. Would somebody give me a value for 2,000 over 5.42 plus 2 pi times 5.42 squared? What'd you get? 553.6 square centimeters. Square centimeters is very, very small, so let's make sure that we get another opinion. Okay, we got another opinion, so if it's wrong, it's your guys' fault and you're fired. So it's looking like dimensions of 5.42 by 34 should minimize the area of that can, leaving us with a surface area of 554 square centimeters. So I hope this video helps demonstrate how to optimize function. This video here is dated, what are we? We're around June 2016, before the fall elections here. So depending on how the fall elections go and whether Mr. Trump takes over any can factories or not, we might be seeing different shaped cans in the future. Anyway, everybody have a great day.